Welcome back to Bargaining 101. I'm William Spaniel, and this lecture is on uncertainty with continuous types. I talk about this briefly in the end of Chapter 7 of Game Theory 101 Bargaining. You can check the video description for more information on that. And as a forewarning for this lecture, there is calculus here. If you don't know calculus, you won't be able to get everything here, but I'll try my best to explain what's going on even if you don't know what calculus is or have never had any sort of experience with calculus. Anyway, the overview for what we're doing. Well, before, we had Barbara either have a low outside option or a high outside option. Either Barbara had a small value if she rejected an offer, or she had a high value if she rejected an offer. Today, we're going to do something a little bit more broad. We're going to have Barbara's outside option be anywhere within a fixed range. So it could be a low value, it could be a high value, or it could be anything in between those two values. More specifically, to construct the game that we're going to be looking at here, nature will draw Barbara's outside option from the uniform distribution on 0, 1. So if you're not familiar with uniform distributions, what's going on here is that nature is going to give Barbara's outside option anywhere in between 0 and 1, and it's equally likely that nature will pick one particular value from that distribution as any other particular value. So it's just as likely that Barbara will receive an outside option that's somewhere between 0 and 0.1 as it is that she would receive an offer, or rather an outside option between 0.2 and 0.3, or 0.8 and 0.9, or 0.9 and 1, and so forth. Everything is equally likely under the uniform distribution, hence that name, uniform. Well, Albert, as always in games of uncertainty, does not know Barbara's outside option, and he chooses to offer a value X despite the fact that he's in the dark here. Barbara knows her outside option, and she's going to see that offer that Albert has made her, and she'll choose whether to accept it or reject it. If she accepts, that locks in the offer or the division that Albert proposed, and if she rejects, well, we have outside option values where Albert is going to receive a payoff of A, and Barbara is going to receive a payoff of B, where that B is being drawn from the uniform distribution at the beginning of the game. All right, now let's take a step back here and explain why we actually want to do it this way. Why are we choosing to have this uniform distribution and this continuous probability distribution thrown into the mix? Why are we spending time trying to figure these things out? Well, for one thing, this is more realistic. You could imagine that Albert and Barbara are negotiating over a car here, and Albert doesn't exactly know what type of a vehicle Barbara will get if Barbara rejects his offer. It could be the case that the vehicle that Barbara will buy will be really, really nice, or it could be that it could be really, really bad. But it's not realistic to believe that it's only going to be one of these two possibilities. It could be really, really good, it could be really, really bad, but it could also be anything in between, and it's not exactly possible for Albert to figure out exactly whether it's going to be one value or a different value. So having this continuous probability distribution of values for Barbara's outside option means that Albert doesn't exactly know what's going on here in any particular specifics, other than it could be a value between some low value or a high value. But again, it can be anything in between. So this is more realistic in that sense. Another thing that's going to be interesting, and we'll see this on the next slide, is that in continuous type cases, you don't have to worry about indifference. In the past, we've looked at how we're making assumptions that in a case where Barbara is indifferent or a player is indifferent, that player accepts and does not reject in those cases. And we talked about why that's the case and why this is actually a worthwhile assumption to make and why this is the best way of doing business. And so people who do bargaining, people who study bargaining, are usually very okay with making this assumption. People who are new to this tend to freak out. I'm going to show you, though, that it actually really doesn't matter in this case what we do in those situations where there's indifference. Another nice part about this is that unlike before when we were dealing with those discrete type spaces where Barbara's outside option was either a low value or a high value, the way we computed the solution to that was by actually typing in numbers, calculating values, and then comparing those two values. That's rather clunky. In comparison, we're going to use calculus to go through a very smooth, natural progression of math that will just magically plop out the solution. So it's got a cleaner, more natural solution when we have continuous type spaces, which is nice if you're a fan of mathematics. And lastly, and I think by far most importantly, is that continuous type spaces are the basis for what's known as the Myerson-Satterthwaite theorem. We'll get to that in later lectures, actually pretty soon. The preview of this, though, is that Myerson and Satterthwaite basically figured out that you can't get good bargaining to occur no matter what you possibly do. It's really interesting. We'll talk more about it in later lectures. All right, now let's go ahead and solve this game. What's Barbara's problem? Well, we always start at the bottom and work our way up top, so that's why we're starting with Barbara here. Barbara knows what her outside offer is, or rather what her outside option is, and so she's going to compare the offer that Albert is making her to the offer that she would receive through the outside option. So if Albert's offer of X is greater than B, Barbara's outside option, Barbara will accept. If X is less than B, she will reject. And in this last case, if she's indifferent, or she's going to be indifferent when X is equal to B. So X is exactly equal to B results in indifference for Barbara. The reason that this doesn't matter is that when Albert is calculating his payoff, about what he's going to get if he offers any given amount, the probability that he'll run into this type where Barbara has an outside option of exactly equal to the offer that he's making is 0. And that's because there are infinitely many types or infinitely many values between 0 and 1, that interval that we were drawing Barbara's outside option from. So the probability of actually hitting any one particular value is equal to 0, which means it doesn't even impact Albert's utility as he's trying to calculate whether one offer is better than another offer. So as a result, we don't really have to even explicitly state what's going to happen in this case where Barbara is indifferent, because the probability of actually encountering the situation in real life is equal to 0. It literally doesn't matter. All right, so now let's go to Albert's decision. We know what Barbara is going to do. She accepts if X is greater than B. She rejects if X is less than B. Now we can figure out what Albert needs to do here. Albert doesn't know Barbara's outside option, but he does have a lot of information. He knows what the likelihood of each of those types is, and he knows what each of those types will do for any given offer that he makes. All right, so what that means is that Albert can construct a utility function. And when he does this, he's going to encounter a risk-return trade-off. He knows that if he demands more, he's going to get Barbara to reject more frequently, but in the times that she accepts, that's going to be better for him. And in contrast, if he demands less, well, Barbara is more likely to accept, but this results in a smaller share of the deal. So this risk-return trade-off, which we've seen before, which is familiar to us, is going to pop up again in this slide right here. So if we actually explicitly write out Albert's payoff is the probability that Barbara accepts times 1 minus X. 1 minus X is the remainder of the deal that he proposed to Barbara. And then on the other half, there's some likelihood that Barbara is going to reject that offer, and Albert will receive a payoff of A, his outside option in that case. Okay, so in order to actually be able to figure out what's best for Albert here, we can't just leave the probability of accept as PR accept and the probability of reject as PR reject. We actually need to figure out what those values are. Fortunately, this isn't that difficult given the fact that we have a uniform distribution. That's why I chose to illustrate what's going on with continuous types using a uniform distribution, because this next part is going to be fairly simple. All right, let's start plugging in numbers and see what happens with the probability of accept reject given those values that we plug in. Imagine that we had X equal to 1/2. Well, remember that Barbara's choice here, she rejects if her value for her outside option is greater than the value that Albert is offering her, and she accepts if her outside option is worse than the offer that Albert is giving to her. So in this case, when X is equal to 1/2, when the offer Albert is proposing is equal to 1/2, remember that every single possibility on the 0 to 1 interval is equally likely, which means half of the types are going to be below 1/2 and half of the types are going to be above 1/2. There are equally many numbers less than 1/2 as there are greater than 1/2 on the 0-1 interval. So in this case, the probability of accept is equal to 1/2 and the probability of reject is equal to 1/2. If we think of one other number, it should be clear what's going on here pattern-wise. If you make an offer of 1/3, Albert will have Barbara accept his offer 1/3 of the time, because the number of types Barbara is that has an outside option of less than 1/3 is equal to 1/3. And the number of types that Barbara has, or that Barbara could be, that have outside options greater than 1/3 is the remainder, or 2/3. So what that means is that the probability that Albert has his offer accepted is actually equal to x, and the probability that the offer is going to be rejected is equal to 1 minus x, which means we can take those values and replace the English letters, the probability accept and probability reject, with x, because x is equal to the probability of acceptance, and 1 minus x, because that's equal to the probability of Barbara rejecting his offer. All right, well, now we have a very clear mathematical function, and so we can think about what this actually looks like. Here I have drawn a graph of this function when a is equal to 0.25. So your x-axis here is your offer size. That's why I've focused this graph between 0 and 1. That's the possibilities of offers that Albert can make to Barbara. And our y-axis here is going to be Albert's payoff for any given offer that he makes. All right, and that blue line then is mapping your offer size to Albert's payoff. What do we see here? Well, we see that Albert's offer, if it's very small, is going to produce an okay payoff for him. If Albert's offer is very large, well, that means he's not going to be receiving any of the deal, and so that's going to be very bad for him. And somewhere in the middle, Albert's payoff is going to be the highest. If we draw an arrow to where that hill is the highest, it looks like the hill is the highest when x is equal to somewhere between 0.35 and 0.4. So the offer that corresponds to where that peak is the best possible offer for Albert. Now, there are a couple of downfalls to trying to figure out what Albert's best payoff is, or Albert's best offer is, by looking just at this graph. One problem is that in order to create this graph, I actually had to have a equal to 0.25. I actually had to assign a value for a. If we want to try to solve this more generically for any value a, I can't just draw a graph like that. It's going to be a little bit more complicated. The second issue is that, well, we've narrowed it down to being somewhere between 0.35 and 0.4. That's still not exact. If we were to try to tell Albert, hey, Albert, you should offer this amount, we couldn't give him very detailed instructions. So Albert might come back to us and be like, well, can you do a little bit better for me? Can you give me an exact value? I'd really like to maximize my payoff. That would be nice. Well, fortunately, there's a way to do that. Fortunately, we can figure out what Albert's payoff is for any a, and we can be very exact, figuring out the exact optimal offer for Albert. How can we do that? Well, if we look at this graph, notice that the slope of Albert's payoff function is equal to 0 at exactly one place, and that one place is where Albert's payoff is maximized. If we go anywhere to the left of where this maximization occurs, the slope of that line is positive. It's gaining ground progressively. And if we go anywhere to the right, that slope is going to be negative. It's losing ground progressively at that point. It's only 0 right where Albert's payoff is maximized. Now, this is where our calculus is going to come in. Remember, calculus allows us to take derivatives, and those derivatives are giving you the slope of a function at any given point. It's the instantaneous slope of a function at any given point. Well, let's think about this for a second. If we take the derivative of our utility function, that derivative is equal to 1 minus 2x minus a. That's what happens when you take the derivative there. Just trust me. The derivative with respect to x is 1 minus 2x minus a. And this derivative function, again, is giving us the slope of the line at any given point x. Well, we want to know where this slope is equal to 0. Because if we know where this slope is equal to 0, that is the optimal offer. This is what calculus is doing for us. It's giving us a very smooth way to figure out where the optimal offer is. All we need to do is take that derivative and then figure out where that derivative is equal to 0. And that will give us the x that maximizes Albert's payoff. So if we set the derivative equal to 0 and we solve for x equal to 1 minus a over 2 is the optimal offer for Albert. Albert's payoff is maximized when x is equal to 1 minus a over 2. So that is how you solve these continuous probability distributions with continuous types when we're looking at bargaining games. So just to recap here, our solution strategy is to first figure out what Barbara's strategy is, figure out what player 2's strategy is, derive player 1, Albert's utility function, using the information about what player 2's strategy is. Then you take the derivative, you set that derivative equal to 0, and then you solve for x. And that x is going to be the offer that maximizes your utility. Whatever x, when you set that derivative equal to 0, whatever x solves that function is going to be your best possible offer strategy if you are the first player. All right, so this was a little bit complicated, and that's fine, but this gives you a flavor for what's going on with continuous types. It gives you the solution strategy on how to solve these sorts of problems, and most importantly, this is going to give you some flavor and some intuition about what's going to go on when we reach the Myerson-Satterthwaite theorem, which we'll be doing very soon. So I hope you enjoyed this, and I hope to see you next time. Take care.